Once you are accustomed to the software stack, the SoDa Replicator itself is intuitive. Instead of reinventing the wheel, the replicator merges tools and replicability conventions. To get started, we visit the replicator's GitHub repository. By default, we land on the main branch. This main branch contains the template filled with example files. Dummy R and Python scripts, text documents, and datasets illustrate how to use it. The template to download is the one on the clean branch, which corresponds to the main branch with the examples removed. The replicator consists of 3 top-level directories: code, data, and paper. Code contains empirical analysis code, that is R, Python, Julia, C++ scripts, etc. Data stores datasets. And paper holds our markup, that is our manuscript and presentation with their respective figures and tables. The template presents the 3 directories in a single repository to facilitate the download. However, this is not how users set it up on their system. As a replicator user, we utilize the 3 folders as separate entities. More specifically, we manage code and paper as individual Git repositories shared through GitHub, and data as a regular folder shared via a cloud storage service like Dropbox or Google Drive. We keep the data folder out of Git because Git is designed to handle small text files, not a terabyte of datasets. There is also no need for version control on our datasets because any change in the processed data results from changes in our scripts. Code and paper are 2 separate Git repositories because the workflow of working on a manuscript is distinct from a workflow experimenting with the empirical analyses. Combining them can result in confusing Git histories and branch structures. To keep the 3 folders in the same parent directory, despite the different sharing type, many users store all of them in a cloud folder, but only share the data directory through the cloud provider. An alternative solution is symbolic links. The code directory is divided into 3 subfolders: .github, analysis, and data prep. We can ignore the .github folder. It contains the GitHub Actions workflow enabling automated AI checks. Template users do not need to edit it. The important directories are the other 2. Data prep contains scripts converting raw input data into an analysis-ready or regression-ready format. The analysis folder entails the scripts loading the analysis-ready files, running estimations, and turning them into figures and tables used in the paper. Users should create subdirectories within both data prep and analysis when appropriate. For example, empirical projects often combine datasets from various sources. We can create a folder per input source within data prep that contains all steps specific to individual datasets, prior to the merging stage that fuses all data together into the analysis-ready format. The checklist file holds the points for the AI to evaluate. We will come back to it as we walk through an example. The data directory is split into 4 folders: Raw, Interim, Analysis, and Literature. Raw hosts the unmodified input data as we download them from the publisher, together with their documentation and information on when and where we downloaded them. Each input dataset goes into its own subfolder within Raw. Analysis contains the final, regression-ready datasets. Interim is a folder for projects with longer data cleaning pipelines, which do not directly go from raw input to regression-ready format but have to generate intermediate files. These intermediate files belong into the interim folder. The literature folder is the place to store journal articles and working papers which are relevant for our paper. These PDF documents are not text files and do not need to be version controlled. Hence, they neither belong into the code nor the paper repositories. Like the code directory, paper hosts a .github folder, enabling automated AI checks and a checklist telling the AI which criteria to evaluate. The 3 folders in which we save our LaTeX code are Results, Draft, and Presentation. Draft comprises the official manuscript, and Presentation contains presentation slides. Results encapsulates 2 subfolders: Figures and Tables. Our analysis scripts in the code repository directly write their output to these 2 folders. Results.txt aggregates these outputs in a single document and serves as a space for preliminary thoughts that we do not want to incorporate into the paper. During the exploratory research phase, It is common to run many analyses in figuring out what theories that data may support. Results.txt is the file to throw all of these results and respective comments into. As a new user, we download the template to our machine as a zip archive. We do not clone it through Git because, as mentioned, we do not use it as a single but multiple Git repositories. On our machine, we extract the archive. Here is the way to do it from the command line on Linux. On Windows and Mac OS, most users do it through the graphical functionality built into file explorers. If you are struggling with the default tools on your computer, have a look at the 7-zip software. We rename the unzipped directory to the name of our research project, Population Weather in this example. Again, on Windows and Mac, we usually do this right in the File Explorer window. The next step in our research project relating the weather in Australian cities to population size is heading over to VS Code and opening the code folder in the extracted directory. To enable relevant functionality, we trust the authors. Once the folder is open, we see its contents on the left-hand side. We open the terminal for the Git Setup. As explained in the tool's introduction, Windows users need to explicitly select the Git Bash terminal, while Linux and Mac users can stick to the default. In this terminal, we initialize a new Git repository with Git init. We add the contents to the staging area and commit them to the local repository. To connect the local repository to a repository on GitHub, we first have to create a new repository on the platform. We name the repository after our research project Population Weather and append _code to distinguish it from the paper repository. We fill in a description and set visibility to private. GitHub displays the connection page with instructions for linking our local repository to its GitHub counterpart. We copy the first line and switch to VS Code. In the terminal, the code connects the two repositories. Since we have already committed the contents, we are ready to push them to GitHub. After refreshing the website, it displays the uploaded state. Next, we repeat the same steps for the paper folder. Hence, we open it in VS Code. We trust the authors. And we open the terminal. In there, we initialize a new repository, add the contents to the staging area, and commit them to the local repository. On GitHub, we create a new remote repository. We name it according to the research project's name, suffixed with _paper, put in a description, and set the visibility to private. In VS Code, we paste the line from GitHub into the terminal to establish the remote link. And we push the local state to the platform. Again, GitHub reflects the changes on the website. In both GitHub repositories, we grant our co-authors access by adding them in the Collaborators menu under the Settings tab. Once our collaborators have joined, we work on the AI checklists with them. The template comes with predefined checklists for both code and paper. Because there is no one-size-fits-all, we need to customize these lists for our research project. We include all points that we want AI to evaluate for us at some points and toggle them on or off with an X in the checkbox. The AI is limited to the context of our repository. The AI in the code repository cannot see the datasets in the data folder or the manuscript in the paper repository. If you want to grant the AI access to these other scopes, you need to amend the GitHub Actions workflow in the .github folder and insert authentication tokens into the repository's secrets. For the AI checks to work, we need to obtain an API key, which we obtain at console.anthropic.com. Once authenticated, we navigate to the API keys menu and create a new API key. The name can be whatever. We copy the key, return to one of our GitHub repositories, and click on Settings, Secrets and Variables, Actions, New Repository Secret. The name here is not the one from the Anthropic site. The secret's name must be exactly the one we show in this form, Anthropic_API_key. Paste the key under Secret and repeat the same steps for the other GitHub repository. After we add it, the new secret appears in the list. We can now use the key in both issues and pull requests. As a demonstration, we create an issue that triggers the AI with the @Claude function. The @Claude call initiates the AI check. The remaining text is the prompt. After a few seconds, we get a comment on the issue notifying us that Claude is working on it. The comment evolves over time and can take some minutes to complete. The replicator template does not impose runtime restrictions. To limit the cost of these checks, you may want to add the max turns flag to the GitHub Actions workflow. Monitor the cost on the Anthropic website and adjust your utilization of this feature accordingly. Once Claude is done, it prints its output into the comment. While it is perfectly fine to use the replicator template without AI checks, they can enhance productivity. As outlined during the tool's introduction, issues and pull requests are, of course, much more than a place for AI output. Regular, non-AI issues and pull requests are essential for collaboration in co-authored research projects. The next step in our example is to fill the repository with content. To avoid later replication problems, we set up a virtual environment before writing any code. Virtual environments record the versions of the packages and of the programming language itself that the project employs. With this system, code produces the same results years after it was written. In Python, both venv and conda provide this functionality. In R, we use the renv package. For consistency, we illustrate the R steps in VS Code. On your side, you are, of course, free to run this in RStudio, Positron, or other software. After the package is installed, we initialize a virtual environment for this project with renv in it. We enter Y to confirm. The function creates a renv.lock file and an renv folder. We do not edit these files manually, but through package functions. Back in the Bash terminal, we add, commit, and push the new files. The renv folder includes a git ignore file since only part of the contents should be shared. It, for example, makes sure to upload package version information, but not the source code of the R packages installed in this project. Opening the project in a new R session automatically loads the virtual environment. In this environment, we install the R packages for our empirical code. We confirm the installation with Y. The virtual environment lists packages in the specification when at least one R script in the project loads them. So, for the just installed data table package to be included, we need to create a script that attaches it. We create a folder and an R file inside the data prep folder using the Explorer buttons. It is good practice to generate input dataset specific folders inside data prep to cleanly separate the initial data processing scripts. In our example, we create a file to clean population data. Loading a package alone is not enough. We need to call renv snapshot for the tool to scan the project and insert data table into the virtual environment definition. That scan only captures regular require and library calls, not package loading wrapped in an apply function. We confirm the package listing with Y. After the snapshot command, we see data table listed in renv.lock. When our co-authors pull this renv.lock file from GitHub, they just have to run renv restore, and the virtual environment installs the exact package version specified in the configuration. Therefore, we push the changes to GitHub. Assume that we have cleaned all data and have assembled our analysis dataset. Now, we want to generate some summary statistics and insert them into the paper. For our code to work identically on all machines without further modification, we exclusively use relative paths. Because the paper directory is in the same parent folder as code, we go up one level with the two dots and then all the way into the results tables folder. For replicability, it is important to export tables and figures in their final format in which they appear in the paper. There should be no manual editing after R, Python, etc. have exported the file. We switch to the paper repository and find the export in the intended folder. In results.txt, we import the table with a relative path as well. We build the document and see the rendered table on the first page. The SoDa Replicator templates default Git ignores exclude most LaTeX files, including the PDF output from Git. Those are the files depicted in dark gray. You can amend this setting by adjusting the Git ignores. Now, it is time for you to give the beginner-friendly replicator template a try. The link is in the description.